Alright, we have a very short video today. We are going to talk about static equilibrium and then look at a quick example. Static equilibrium is the idea that an object is at rest and it is going to stay at rest. So what we want to think about here is, if an object's at rest, what is required to remain at rest? And if you think back to our force chapters and our force analysis, the requirement was that the net force acting on the object had to add up to zero. The net force was zero. That would give you zero acceleration, so the object, if it was at rest, would stay at rest. That was back in force analysis when we didn't consider extended objects and we didn't allow for rotation. If you look over here at my example, I've got this rod and I've got two forces, one over here on the left, one over here on the right. The two forces are the same magnitude but opposite direction, and so the net force on this object is zero. But this object will not remain at rest. It's actually going to begin accelerating rotationally, right? It's going to spin up, so it's going to start rotating. So that means even though the translational acceleration was zero, the angular acceleration is not zero. And so what we need to do is add an additional constraint, and that constraint comes from our torque analysis, that if we want something to be at rest and remain at rest, if we want it to be stable, if we want it to be in static equilibrium, then we also need the net torque, which should add up to I alpha. We need alpha to be zero, so we need the net torque to be zero. So it's those two constraints that we're going to use to now investigate scenarios when an object will remain in static equilibrium. So I've got an example here to show exactly how we should begin to approach problems where we want to require an object to stay in static equilibrium. Again, back in force analysis, that would literally just be identify forces and apply Newton's second law. But now, since we've got rotation, we're going to see there's an additional step. So I've got this board here that's just resting on these two supports. It's free to rotate. And then I've got a person standing at the middle of the board. Now the board has a length of 4 meters. The board has a mass of 5 kilograms, and the person has a mass of 60 kilograms. And what I want us to do is I want us to find the supporting forces. So there's a force associated with both of these supports being in contact with the board. What are those supporting forces that are required so that this object stays in static equilibrium? So the first thing I'm going to do, so the first step here is identify forces. And I'm investigating, in this case, the forces on the board. That's what I'm interested in. And so rather than treat the board like a point, I now care that it's an extended object. So what I'm going to do is I'm going to draw the forces exactly where the forces are applied to my object. So I've got this force, I'm going to call this F1. So that's the support force from the support on the left. I've got F2 over here. That's the support force, so pushing up on the board from support 2 over on the right. I also have the weight of the board down. And then I also, at this same location, have the force of the person down, right? They're standing on the board. And if we do force analysis on the person, you would get that the force of the board on person, you would get that force has to be the same size as the weight of the person. Right, so that's just to remind ourselves. So this is a separate free body diagram just for the person. And then I'm going to use Newton's third law to connect the force that the board is pushing on the person, to connect that to the force that the person is pushing on the board. All right, so I've identified my forces. I've got 1, 2, 3, 4 forces acting on my board. And the first step, why not just apply Newton's second law? So this is actually the same second step that you would do with just force analysis. Let's see what happens. So if I apply Newton's second law, that means the net force in the y direction, right, there are no x forces. The net force has to add up to ma, and in this case we need to be in equilibrium, so we're going to set that equal to 0. So I've got plus F1 because it's up. I've got plus F2 because that's also up. I've got minus the weight of the board, and then minus the weight of the person. Again, this is actually the force of the person pushing on the board, but from our analysis of the person, we know that that's equal in magnitude to the weight of the person. And then this has all got to add up to, again, ma, but since we're in static equilibrium, that's got to add up to 0. So what we get from Newton's second law is that the combined two forces, F1 and F2, have to equal the weight of the board plus the weight of the person, which in this case, the masses are 65 kilograms total times 9.8, that's 637 newtons. So the problem here is that the two forces, F1 and F2, have to add up to 637 newtons, but we don't have, from this analysis, we don't have any sense for how the forces are split up. Is it that 637 newtons of force is F1 and F2 is 0? Is it the other way around? Is it split in half? We have no way to determine that, and so that's where we're going to go and apply our second constraint. So step 3, apply rotational version. Of Newton's second law. Now, the key thing here, so that means net torque got to add up to 0. And so the key thing for torque analysis is picking a rotation point. Now, when you're looking for the net torque, your rotation point, you can choose whatever you want. You can choose some spot out here. You can choose this spot right here. You can choose any location. The net torque is going to be the same value. The problem is, if you choose a location like out here, then you're not going to be able to do the calculation because you're not going to know how far away the forces are. So you want to be smart about where you choose the rotation point. And so we want to think about our extended object. Again, we've got 4 different forces acting on the object, and 2 of them, these 2 right here, we actually know the magnitude of, and F1 and F2 are forces that we don't know the magnitude of. And so we want to choose a rotation point that allows us to most simply analyze the torque. And the way that we typically do this is we pick a rotation point that's at the location of one of the forces that's unknown. So in this case, I've got 2 options. I could pick over here as my rotation point, or I could pick over here. So I'm going to pick the first one that I've identified. Now, the reason that this is a good choice is because now this force F1 that I don't know the magnitude of, it's being applied at a distance of 0 meters from my rotation point. And so the torque generated by F1 about my rotation point is 0. So it's not actually going to factor in to my calculation. So let's look at the net torque. So I've got this force doesn't factor in. Now I've got these 2 forces, and so I'm going to have a torque term from both of those. And if you think about my rotation point being here, if you have forces in this direction, that's going to cause or would cause rotation in that direction. Remember, this clockwise rotation is a negative torque. So I'm going to call these negative torques. Now, both of these forces are 1 meter away. In one case, I've got the weight of the board, and then the angle between the radial line and the force is 90 degrees, right? So that's 1. The distance to the other force, same distance, 1 meter. Now remember, the force of the person is really equal to in magnitude, the weight of the person, and then sine of 90 degrees. And then I've got one more force way out here. This is in the opposite direction, so this would cause rotation that way, so we're calling that plus. So plus, and now I've got 3 meters away, I've got this force F2, and again the angle there is 90 degrees. And all of that has to add up to 0. So I'm going to combine some terms here, and I'm going to move these. These are both negative. I'm going to move them over to this side. So I've got 3 meter times F2 equals 1 meter times, and then I'm going to combine the weights, which is 637 newtons. So this tells me that F2 has to equal 637 divided by 3, and we get 212 newtons. So that is F2, that's the force over on the right support. And then we can immediately determine F1. We can immediately determine F1 because we know that F1 equals 637 newtons minus F2. So F1 is going to equal about 425 newtons. And if we think about this result, we've got the left support providing a greater supporting force than the right support, and you look at this, and the person and the weight of the board is closer to the left support than the right support. And so that makes sense that this support then would be providing more support force. Now, you could imagine if you moved this support directly underneath this location, well then this support would actually be supporting the entirety of both of the weights, right? So it has to do with the location of the forces that are being applied to the board, and then how far away the supports are. Now, one of the requirements for stability is that the center of mass of the system, so we've got the board and we've got this person. So the center of mass of this system is located right here. That's because the board is uniform, so the center of mass is right in the middle, and then the person is standing over top of it, so that doesn't change the center of mass. And so the requirement for something to be stable is that the center of mass needs to be supported. It needs to fall within the supports of the supporting structure. So if this person walks this way, there will be a point where this person walks far enough that the center of mass of the system gets directly over top of this support, and then eventually gets beyond this support. And at that point, if the center of mass of the board, person, system is out here, all of a sudden this thing will no longer be stable and it'll come crashing down. It'll begin to rotate. Right? So we're going to use that piece of information that the center of mass of the system needs to be within the supports. We're going to use that to determine if something is stable or not in future problems.